Hi everyone, this is the next lecture in Geology 3104C at the University of South Florida. This is Sarah Sheffield, and today's lecture is going to be on morphometrics and ontogeny. So changes in shape and growth. So we're looking at a trilobite growth series on this first slide, and we see that there's significant changes to the specimen from the younger to the older. All right, so we're going to talk a little bit about how that happens and why it matters to us in paleontology. As a quick reminder, ontogeny is growth and change of the individual during development. All right. Evolution, however, is descent with modification. These are two separate concepts, so a lot of the times people will confuse the two to talk about the evolution of an individual. So I wanted to remind you that natural selection, evolution by natural selection, is only acting on populations. So individuals make up those populations, but one individual does not evolve in a lifetime, biologically speaking. This leaves Pokemon completely out of the question here. Evolution occurs because individuals mate, they reproduce, they pass on their genes. That is how evolution is happening. So remember not to confuse those two terms. All right, so the first type of growth that we're going to talk about today is growth by accretion. Accretion means addition, adding things. So this means that growth occurs by adding on to existing skeleton in layers. We can track these layers pretty easily, so think like tree rings and things like that. And they commonly manifest just like tree rings in growth lines. So we'll see this a lot in mollusks, brachiopods, corals. Sometimes we'll see this in echinoderms. It depends on who we're looking at. So here are some examples. We can see the growth lines here of this mollusk and on the brachiopod. The brachiopod's on the right, the mollusk is on the left. And we can see those growth lines. We can see different alternating bands. Like we did with the corals assignment earlier, we know that these can actually help us track time. They can help us track paleoclimatic conditions, all kinds of really interesting things. It's probably one of the easier growth mechanisms metabolically. It uses the least amount of energy comparatively. However, only limited shape change allowable. And this will be important because shape change can help us identify functional changes. And a lot of the times shape changes do mean that functionality needs to change, thinking like tadpoles and frogs and their ontogenetic stage. That great shape change indicates a large change in function and environmental use that couldn't have happened by accretion. And one thing to note is juvenile morphology is incorporated into adult forms, which means it can be fairly easy to identify the juvenile forms of the species. Addition of new parts. New parts are added throughout ontogeny. This is a little bit different. This can often leave us with drastic changes in shape, which can indicate large changes in function as well. And we see this a lot in invertebrate groups like echinoderms and arthropods. So again, here we have our addition of new parts. All right, so here is our wee baby trilobite here. We see that it's got a lovely cephalon here, the head piece. And we see then it starts adding on to, we've got the pygidium right there, which starts adding the thoracic segments, all right, and developing across the three lobes here, giving it its lovely name, the trilobite, and the spines are going to develop through time as well. What that means, though, so we take a look at this holaspid, that is the final growth stage in a trilobite, and we take a look at the proaspid, the first one, it can actually be really difficult to figure out which one, the juvenile form of which one. Is it just a really small specimen of another species, or is it a juvenile of the same? It can be really difficult to figure that out. Here's an example of echinoderms too, growing by addition of new parts. So this is Eumorphocystus. This is a blastozoan echinoderm. This is one of the most beautiful fossils ever made, and I am not biased at all when I say this. So what we're looking at here are these plates. New plates are inserted as the specimen grows. All right, and we see the smaller plates being inserted. So the first generation plates are the oldest, those are the largest plates. And we see the second generation plates being added and crowded into the theca, which is known as the body. Nautilids also do the same thing. So remember, each chamber is actually added as the organism grows. The organism lives in this part of it, right? And new chambers are added. So this is also fairly easy metabolically. Does allow for dramatic changes in shape because it can add new shapes that allow for different functions. And juveniles or juvenile morphologies are incorporated into adults, but that can change a little bit more drastically. We also have molting. Old skeleton is shed, replaced by new skeleton. Oftentimes can lead us with drastic changes in shape. This is a really cool function about it. It's typical of arthropods, and what it can do is it can show instar ontogenetic patterns. We're going to take a look at what that means. And instar is the term that we use for the developmental stages of arthropods between each molt. This is going to rely on our current use or current knowledge of arthropods. What I mean by that is when you shed your exoskeleton, it takes quite a bit of time for your new one to fully form and to fully harden. When you first emerge from your molt, your body's pretty squishy. The calcium carbonate hasn't hardened yet around you, or whatever your exoskeleton is made out of, depending on if you're an insect or if you're a lobster. So the record of instars, so that before when they are actually hardened, it's actually pretty bleak, as you can imagine. So we have to look at modern organisms to better understand the instar stages. So what do you think a trilobite growth series would look like then if we have instars that aren't fossilized? If we took a look at a graph of trilobite growth from smaller to larger, do you think it would be a continuous jump or a continuous graph, or do you think there would be jumps in it when we have those instar stages? Think about that question. So here is another friend of ours, the trilobite. This one has some wild spines coming across it, lots of details here. And what we have here are the different stages. And you see that there's incredible changes in shape that go through, along with addition of parts. So molting and addition of parts here. And we'll talk more about how we can combine those later. Molting is pretty difficult metabolically. A lot of organisms can actually die from the amount of energy that it takes to molt. So for a good example, we know this because of modern critters. So for an example, my mom, who's a former preschool teacher, she decides one day that she just really needs a pet tarantula. Never mind the fact that, her kid is terrified of spiders. If you're listening, Mom, I'm not sorry. This is my revenge. So my mom adopts Bitsy. Yes, Bitsy, like itsy bitsy spider, as I said, former preschool teacher, right? And Bitsy hangs out with my mom. She just sits on her shoulder all day as we're walking around. It's absolutely horrifying, and I'm sure has nothing to do with the fact that I pretty much stopped sleeping in high school, right? So one day, Bitsy just doesn't move. And I'm thinking, okay, she's dead. She wasn't. She was molting. She laid perfectly still for quite a long time, getting the energy up to molt. This happens differently across different groups of arthropods, but in tarantulas, it required extreme stillness for quite some time because any sudden amount of stress might actually kill a tarantula. So Bitsy survived many rounds of molting, and if you were wondering, my mom decided to get a second one, and yes, she named it Itsy. So she had the itsy bitsy spiders. It was great. So molting is an interesting form of growth because it can allow unsurpassed ability to change shape. One thing that we can also do is we can regrow body parts that were once lost. For example, lobsters can grow back their own claws if they were lost. Juvenile morphology is not in adults, right? We lose that information, unlike when we have growth lines or something like that. And juveniles shed much more frequently than adults, which we should know because juveniles, of course, grow much more quickly, typically. So lobsters will molt up to once a week sometimes in their juvenile phase and then move towards closer to once a year as an adult. Now, as I said, it's energy costly, extremely energy costly. And it's also a problem because if you are shedding your exoskeleton, it takes a couple days for your new one to firm up. So if you're a lobster or something like that, you all of a sudden have a soft body, which is perfect for predating, right? So a lot of lobsters will actually hide right after molting to be able to avoid being predated. It takes quite a few days for your exoskeleton to firm up. So that might also explain sometimes the jumps that we see in the trilobite growth record, because we probably have a lot more predation of our critters in the instar phase than we do when they are with their exoskeleton. Now, what if you just get stuck? Not a question probably you ever thought you needed an answer to, but what if a lobster gets stuck in its exoskeleton during molting? It can happen. For example, here's a horseshoe crab who got stuck during molting and it actually died. This one, it likely interfered with the breathing capabilities. You can also rip off body parts, so you can lose a claw or eyes while you were molting. So if you wanted to check out a juvenile crab molting, I'm sorry, it should say lobster, I think. I can't remember now. Anyways, you can check that out here at this video. All right, so growth by modifying existing parts. The old skeleton is remodeled during ontogeny, and it comes with some shape changes, and it's typical in vertebrates and echinoderms. So here we have a Pachycephalosaurus skull. This is a dinosaur, all right, and we can see that there are minor changes to the skull during ontogeny, which is a pretty interesting thing. And now a lot of the skull change shapes deals with these spines around the rim of the head. For a long time, we really weren't sure what the heck was going on with Pachycephalosaurus. Of course, this is a weird head. Some folks thought it was for mating purposes, like, hey, look at the dome on my head. Let's go get dinner and get to know each other. Or maybe it was for defense. A lot of folks thought there was no way they were butting heads like modern day elk could do, because that would lead to death. But a lot of the trace fossil record shows that there were bone lesions left behind on Pachycephalosaurus skulls, so perhaps it was actually for butting heads. Humans also modify their bones through growth. One of the things that we do is we actually fuse our bones together. So why would we do this? So for those of you who have spent time around a human baby, you know, don't poke their heads, right? That's a big thing. The reason for that is that their bones have not actually fused, and you can cause them damage by poking their heads. So why would that happen? Why would evolution say, you know what, let's ship out this infant with a head that can be squashed real easily? Well, it's actually a really important survival tactic. As our brains got bigger, our skulls got bigger to accommodate this. But we still have a very specific pathway that humans have to take to get outside and live in the world, right? They have to pass through the birth canal. So the birth canal didn't get much larger. And in fact, it got kind of more restricted because we were walking upright. So human babies actually have a softer head so that it can escape the birth canal without breaking anything, leading to survival, even with the larger brain. So that's a really important reason to have a non-fused head. Does not make this picture of the infant less creepy, though. I grant you that. All right, so it's difficult metabolically, and juvenile morphology is not incorporated into the adult, which means that I can't look at an adult skeleton and see how it would have changed as from child to adult. Now, a lot of organisms do grow by different combinations of growth. For example, arthropods grow by molting, and that should say molting, my apologies, and adding new parts. Echinoderms can grow by accretion, sometimes modifying existing parts, adding new parts. So lots of different ways that this can happen. So again, here is our good old friend the trilobite. We know it is growing by molting. Here are the different stages. The instars would be between these stages of growth, and it's adding different parts, thoracic segments, and then spines later, showing great shape change. Here's an echinoderm. This is another blastozoan. Beautiful. It is growing by accretion, right? We see these accretionary growth lines here rimming these thecal plates, the body plates. We also see second generation plates, addition of new parts being inserted through growth. Now, one bias in ontogenetic studies is that we often tend to think of critters in the fossil record as adults. We often look at a new fossil and say this must be an adult. But sometimes it's actually just a juvenile of a species we already have. But because of shape changes, it can be really difficult to track that growth. So we have to do growth studies to figure this out. Really famous example of this is Nanotyrannus. This is the current drama in science Twitter, specifically vertebrate paleontology science Twitter, right? There's lots of fights going on about this. So Nanotyrannus is a genus, we think, maybe, we don't know, of Tyrannosaurid, a small Tyrannosaurid, closely related to the T-Rex. However, some scientists have uncovered information that suggests that Nanotyrannus isn't its own genus. It's actually just a genus, or a juvenile, Tyrannosaurus rex. So here we have our adult and juvenile Tyrannosaurus rex. There's a lot of evidence to indicate this Nanotyrannus might actually just be a T-Rex. I am not going to take sides on this argument. I really don't know enough about it, but it is possible that Nanotyrannus isn't actually a dinosaur. It is just a juvenile T-Rex. Okay, so a growth series. You have started doing a growth series already when you measured your brachiopods, but ontogeny can be studied from an ontogenetic series of individuals of the same species. Issues of species identification can be difficult if there's radical changes during ontogeny. So if you can imagine some of those trilobites with all the spines and things like that, it can be pretty difficult to track that through time. Here is one such growth study. This is a crinoid. It's from the Pennsylvanian, otherwise known as the Upper Carboniferous. And we see some changes. Here we have our beautiful little Anisometric. That's its genus name. All right, here's the cup with its plates. Here's the stem, here are the arms. You can see that more plates are being added, all right, through time. And the cup is being modified, right? The parts are being modified through time. So there's at least 2 different types of growth there. So one of the things that we can do is we can track that change. This is an ArcGIS study that was done to track detailed area changes in plates through time. So here's the full growth series. I only showed you the first 3 of those, but you can go back and say, oh, look at those. They're like the exact same. All right. This is not a useful way to use GIS, but there you go. So we can actually track those types of growth changes. Here is a snail growth series, a gastropod growth series, and we can see that here's our baby. It has a much more pointed apex, but we can see different things like the opening of the operculum stays fairly similarly sized. It only grows a little bit, not nearly as much as the rest of the shell. Now we can also study it from a single specimen if it has preserved ontogeny, like mollusks with their growth lines. So there are issues of within population individuals, so there could be variation, but that's why you take multiple samples from an area. Okay, so growth rate. There's different types of growth present. All right, so there's first determinate growth. This is the more common type. This means that growth stops once some set size is reached. Certain genes will turn off when you have reached a certain size or a certain age. Here is my dog Boone as the cutest baby known to man. Look at this little squish ball here, right? He was all belly, no control, very obnoxious. Love him dearly. So regardless of how much food he eats or how many years he's alive, he will stop growing at one particular time, and that particular time is determined by his genes. A skeleton will not continue to grow. So here is adult Boone today. Just as cute, much larger, about 65 pounds larger. So the growth series here, we see Boone as a small puppy here looking very done with this. All right, here he is as a juvenile, a teenager, eating us out of house and home, wearing a birthday hat, making a wish for more food. And here he is as an adult, very annoyed with me. That dinosaur hat here is very tiny, so these are not to scale, just heads up. All right, so indeterminate growth. Growth never stops during an organism's lifetime. It might slow down. Again, just like with Boone here, most of his growing was done in the first year of his life or so. And that's the same with indeterminate growth. Now, many reptiles do grow throughout their entire life. They do change the growth rates, so juveniles will grow faster. There's some debate on whether gators do or do not have indeterminate growth. Some have said that there is growth stoppage as adults, but most of them do seem to continue. So the larger the gator, the older you can assume it is. Okay, so types of growth rates. Isometric growth. Growth is proportional. Anisometric growth. Growth is not proportional. Isometric, you might remember that term from mineralogy. It means all crystal axes of the same length. So it means kind of similar here. Iso means same. It is growing proportionally. Every side is increasing at the same rate. Anisometric growth, growth is growing at very different things. This is the more common type of growth, anisometric. So here we have an old painting. These were excellent examples of anisometric growth. This is supposed to be a baby, though it has the proportions of a fully grown human, and it is very creepy to look at for a long time. There you go. So here are some charts showing isometric growth, which we see in A and B, and anisometric growth, C and D. All right? No matter what that line looks like, it is not growing proportionally in these particular examples. So there's a specific type of anisometric growth called allometry, allometric growth. And that means that different parts of an organism might grow at faster or slower rates relative to one another. And this is relatively common. So for example, let's take humans, because we know humans really well. So human babies are born and they have gigantic heads. right? Especially compared to their torso and legs. Gigantic heads. It's almost funny, right? They have giant eyes. The size of the head grows much slower than the rest of the body because the head started off quite a bit bigger, right? So here we have another example with some more creepy human diagrams. We're really loading up the creepy human diagrams today, sorry. First with the baby skeleton and now this. But positive allometry means a structure grows at a faster rate than the rest of the organism. For example, legs grow much faster than the torso does. All right, these are from Stephen Jay Gould's diagrams in 1966. The equation for allometry is y equals bx to the a, where a and b are constants. You don't need to know that, but that's what it is. Negative allometry, the head grows slowly relative to the torso. Just like we discussed, the head grows much more slowly. Now, why do we have these changing growth rates? A lot of the times, as we said earlier, it has to change for functional purposes. If our bones, human bones or any vertebrate bones, grew isometrically, our bone volume would have to increase much faster than the cross-sectional diameter of the bone. The mass would increase too quickly and it would break. So here what we have are 3 different bones. These are blown up to the same size looking, even though they're not. This is the largest bone. This is the smallest bone. We actually have to add on to our bones width-wise at the same time as they get longer to be able to handle the weight of the body. Without it, our bones would actually just snap. So this growth is the only reason that we are able to walk without our bones breaking. So it's a pretty helpful thing. All right, here are your review questions. I will see you back for heterochrony and evolutionary growth patterns.